Hi guys, welcome back to Data Every Day. Today we're looking at a data set of emails and trying to detect spam in the emails. And we're going to use word embeddings for this. So here are the emails. We have, it looks like 5,000 or so different emails. And we're going to try, each one has a label. And we're going to use word embeddings to send each word to its own vector representation in high dimensional vector space. And then use a neural network to make predictions based on those representations. So let's hop into the notebook. We're going to use NumPy and pandas for working with the data. For pre-processing, we'll just be using the train test split function, and the model is using TensorFlow. So it's a very simple import section here. I'm going to load in the data using pandas.readcsv. We'll get the file path to the CSV file up here, and we'll go ahead and paste that in. And we can take a look. Also get a little more information with data.info. So we have no missing values, and it looks like we're only going to need these two columns. We don't need the file name. So let's go down here and start pre-processing. I'll create a function called preprocessInputs that will take in a data frame, and it'll perform the pre-processing and then return the data frame, and it'll make a copy first as well. So let's store the processed version of the data in X and pass in data to the function. Currently it's just a copy, but now we'll make changes to it. So first thing I'd like to do is just drop the file name column, since we don't need it. So df.drop file name from axis 1, which is the column axis. So this is all the data we'll be using. So what we need to do is convert each of these emails into a sequence of integers, where a single integer represents a particular word. Now you'll notice this is very messy. These emails are extremely messy. We have all these sort of like new line characters and problems going on. But with the approach we're taking, which is using deep learning, we don't have to do a lot of preliminary pre-processing on the text, which is very nice. Because if you were using traditional NLP techniques, you'll have to do so much filtering, removing stop words, removing punctuation. A lot of that is taken care of for us in the way that we're proceeding. So, like I said, that's using word embeddings, where the representations of the words are learned via deep learning. And the reason we don't have to do a lot of pre-processing is because the model can learn which words are similar, and it can sort of learn which words are not important, so we don't have to manually remove them ourselves. Okay, so the first thing I'd like to do, well actually it's the second thing, we already dropped the column. The second thing is to split the data frame into two parts, into X and Y. I'll call it X and Y. X is going to be our inputs, Y will be our prediction column. So category is our Y, and X is just the message column. So let's make Y category column and X the message column. And then down here for now we'll just return X and Y separately. So let's get them over here. Here's X, which is just the messages, and here's Y, which is just the labels. And the indices match up. Okay, so how are we going to transform the messages? So we're going to use a tokenizer from Keras. So alright, let's create the tokenizer here. This is from tf.keras.preprocessing.text.tokenizer. And this thing will basically look at each email, each sentence, and first thing it will do is strip away all punctuation. Next thing it will do is split on white space, so it will separate the words based on white space. And then it will lowercase everything, and then it will rank each word based on its frequency within the data set we pass in. Then it will assign integers based on the ranks to each word. So the most frequent word will be assigned an integer of 1, the second most frequent will be assigned an integer of 2, and so on. So we can fit the tokenizer using tokenizer.fitOnTexts. We pass in the texts here, and the texts are going to be X, which is these messages. However, I actually want I want to fit the tokenizer only on the train set, because you want to build a tokenizer that can be used on unseen data. So using a train test split is a good way to test that it works. So we have train test split first. This will just give us xtrain, xtest, ytrain, and ytest using the train test split function from sklearn. We'll pass in x and y, specify train size, let's give it 70%, keep shuffle equals true so that it'll shuffle before it makes the split, and give it a random state as well. Alright, and then let's return these 4 sets of data, and we'll get them back over here. Alright, so now instead of looking at x train should just be 70% of the data, y train should also be the 70% that corresponds to the messages here. Okay, so let's fit the tokenizer on xtrain. Let's put this up here. Okay, so we pass in xtrain, and once it's been fit, we can actually check how many words are in the whole corpus of text that we passed in with tokenizer.wordIndex. And this is actually a dictionary that maps each word to its integer. So this is the ranking of frequency. So this is the most frequent words in descending order. And so these are all the words in the text. So let's find the length of this. You see how many we're dealing with. So we have 79,000 unique words. And this is actually a problem. If you have too many words, it can actually confuse the model. It can actually make the model perform worse. I find that a range from around 10,000 to 30,000 tends to work well, depending on the data set. In this case, let's use 30,000. So we can specify that in the tokenizer initialization with num words. Let's make it 30,000. So if we run this and fit it, we will still get the same number of unique words in the word index. But when we actually use the transform function from the tokenizer, it will only do it. It will only transform the 30,000 most frequent words, and it will drop all the rest. So we can do this with tokenizer.texts to sequences on xtrain, and that will take each sentence and it will apply the mapping. First, we'll do that in initial pre-processing, like dropping punctuation and splitting. Then it will apply the mapping that we saw on word index. And so each word has its own integer now, given by the word index. So this is actually lagging because it's so big. So we could turn it into a NumPy array to condense the representation of it. And you can see that each one of these is a sentence, and each one of these is a sentence, and each word in the sentence is given an integer. Okay, so this is something we could actually pass into the model. Only problem is it's a variable length, so these lists are not all of the same length, so we'd like to standardize the lengths. For that, we will pad the lists to have zeros at the end, so that they all have the same length. In order to do that, we're going to need the maximum length of a given list. So before I actually get into this, let's actually make a function to do all this for us. So I'll create a function called getSequences. It's going to take in some texts, a tokenizer, a flag that says if it's a train set or not, and the maximum sequence length, which I'm going to initialize to none. So the first thing we do, we pass in the tokenizer that has already been fit. So we assume this tokenizer has been fit already. We create the sequences using tokenizer.texts to sequences on text. And we could return sequences. That would give us what we have right here. Now we want to pad it, so we can use the pad sequences function from Keras for this. tf.keras.preprocessing.sequence.pad sequences, and we pass in sequences. And we also need to specify a maximum length. So this is how long do we want to pad until, and this should be the longest, the length of the longest sequence. So we have this argument max sequence length. Now, if since we only fit on the train set, then if we're doing this to the test set, we have to make sure that we pad the same length as the train set, not the test set. So what we're going to do is, if train equals true, so if we're dealing with the train set, then we want to calculate max sequence length. If we're dealing with the test set, we're not going to do this because max sequence length should have been passed in up here. Because once we create the train set, we know the maximum sequence length already, so we'll pass it in along with the rest of the arguments. But if we are on the train set, we don't know it yet, we're going to calculate it here by taking, we're going to take this list. Let me just call it seq down here so we can just look at this. If we look at the length of sequence of seq, as there's 4,000 different lists in here. Yeah, let's do it this way. I don't want to lag it, but you can see. Okay, you know what I'll do is use this function pad sequences. No, actually I won't. Okay, what we want to do is find the longest list in here. So what we can do is apply a map to this thing. So we want to apply a lambda function to every element in sequence, where each element, we'll call it x, is a given sequence. So this is all the sequences, and then x is a given sequence. We just convert x into the length of x. And then we'll turn this whole thing into a list. And so this is the length of each sequence. Now all we have to do is take the max with numpy.max of this list to get the longest sequence in there. So the longest email is 14,804 words long. So this is the value we'll pad to. So max sequence length should be this thing. Let's put it up here. We're just going to change sequence to sequences, which is the name of this. So we calculate it, and then the max length here is going to be max sequence length. I'll also include padding equals post so that the zeros go on the end of the sequences instead of the beginning. Alright, and we'll store this back into sequences. That should be it. This is the whole function. We've already fit the tokenizer. We pass it in. It converts the texts into sequences. It calculates the maximum sequence length if it's the train set, and then it pads using the maximum sequence length. Alright, so let's do this then. Let's test it out. So get sequences for xtrain, and the tokenizer we fit already. Train equals true, and we don't have to specify the max sequence length if we're doing the train. Alright, and here it is. So let's look at the shape of this. You can see it was padded with zeros. Each sequence is 14,804 integers long, and we have 4,000 different sequences. Alright, so let's do this up in our function. Yeah, I guess it's okay to do it in here. Even though we lose reference to the tokenizer, we're not really going to need it for our purposes. So we'll create the tokenizer. I'll just use the same one we had here. And then we'll fit the tokenizer. So tokenizer.fit on text. Pass in xtrain. We only fit to the train set. And then we will convert text to sequences. And we'll use this using the getSequences function we built. Pass in xtrain, the tokenizer, train equals true, and we're gonna store it back in xtrain after we convert it to sequences. Xtest will also be getSequences on xtest and the tokenizer. The train equals false, and here we specify the max sequence length, and we can actually get it from the shape of xtrain. So the max sequence length here is going to be xtrain.shape sub 1, which is the second dimension of the shape, which is the number of columns, or a number of words in the sequences. Alright, and there we go. So if we run this, we should have, oh whoops, I deleted that. Let's put this above. Alright, so let's look at xtrain. Alright, so these are proper sequences. The shape should have, yeah, each sequence has 14,000. Let's verify that xtest has the same shape. And sure enough it does. Now I doubt in xtest, well actually, we may have had a longer sequence or a shorter sequence, but all of the sequences were padded to the same length because that's what we had in our train set. Alright, so also ytrain. Let's look at the value counts. It's a little better to see. So we have more negatives than positives, but it's not a terrible imbalance. It looks like maybe 1/3 to 2/3 or so. Maybe not even, not that much. Oh yeah, actually just about. So there's like 1/3 positive, 2/3 negative. That's okay. Let us start training. So the input to our model, tf.keras.input, the shape of the input is going to be a single sequence, which is coming in. So let's look at the shape of xtrain. So this value is the length of a given input. So we pass in a single sequence, and then with that sequence we're going to embed the words. So we'll use a Keras embedding layer for this, which takes a sequence, and for each word it will embed it in vector space. Where to embed it, like I said, is learned by the model, so we don't have to worry about that. But we will specify what dimension of a space we'd like to embed in. So the input dimension is the dimension of the original space. If you think of each word as being encoded in a sparse format. So we originally had 30,000 words. There are 30,000 unique words in this dataset. So if we were to sparse encode or one-hot encode one of these integers, it would require 30,000 numbers to encode, because you'd have all zeros and then a single one for every number. So the input dimension is the dimension of that sparse space, which will be 30,000. Then the output dimension is the dimension of the dense space, which is where we choose the dimension here. I'm going to choose 64. It seems that as the task becomes more deep and the relationships between the words become more complex, a higher dimensional output space is required. But for the purpose of spam classification, 64 seems to work just fine. So we'll pass in inputs here. And let's just take a look here what it looks like. So if we look at inputs, the shape coming in is just a single vector of length 14,804. If you look at embedding, you can see that each original integer in that original input is now being represented by 64 numbers. So it's 14,804 by 64. So this is the number of words, and this is the number of numbers representing each word. Now, what we'll do is, after we've embedded it, and this is like a very meaningful embedding because the model learns where to put the words. So the model tends to put them in places that are useful for making predictions. So what we'll do is now take these embeddings and flatten it all out into a single vector, the flatten layer. tf.keras.layers.flatten, pass in the embedding layer here, and then let's look at flatten. All flatten is doing is taking this and multiplying it by that, so it's just taking, like, destacking, unstacking the matrix into a vector. So we have a lot of parameters here. Sorry, not parameters, a lot of neurons. 947,000. And then lastly, let's take all of these and we'll just give each one of them a weight and send it to the final output. So outputs will be a dense layer with a single value and a sigmoid activation. So this is the probability of it being spam. And so all of these are being mapped down into the single value. So this value is a combination of all of these with weights applied and then added together, and then an activation function applied on top of that, which is sigmoid. So this will take a value between 0 and 1, where 1 means, well, the closer to 1 it is, the more likely it is to be spam. Pass in the output from flatten here, and then we'll construct the model using tf.keras.model, passing in the inputs as we specified, and the outputs as we specified. Alright, so let's compile the model. we'll use an atom optimizer. For loss function, we'll use binary cross entropy, since it is binary classification. And for metrics, let's use accuracy, and we'll also use AUC, which is area under the curve of the receiver operating characteristic curve. tf.keras.metrics.auc. The name here we'll just give us as AUC. Alright, and then we'll print out a summary of the model. We got a problem. Oh, I misspelled activation. Activation. Alright, here's the model. So we come in with that single vector. Each word gets embedded as 64 numbers. This whole thing gets flattened down into a single vector, and then all of those numbers get weighted and combined, and then activated to produce a single value as our prediction. Alright, let us train. So I'll store the fit history in history, call model.fit. We're training on xtrain and ytrain, giving it a validation split of 20%. We'll give it a batch size as well of 32 should be fine. Let's train for 100 epochs and give a callback function. tf.keras.callbacks.early stopping. And here we will monitor the validation loss and set a patience threshold of 3. So when the model's validation loss stops improving for 3 consecutive epochs, we'll stop the training and restore the weights from the best epoch. Alright, before I run this, I'm going to enable GPU acceleration, which actually I'm not sure if it's necessary. Let's see. Maybe, I don't think with word embeddings it's absolutely necessary. Yeah, it's okay. It does go faster with the GPU, but it's not going to be terrible. Alright, so I will pause the video and resume when this completes. Alright, so the model has completed training, and you can see we're getting extremely high values for accuracy and AUC. So let's get the results down here. First we'll just call model.evaluate to get the metrics. So pass in x test and y test, and we'll store that in results. Verbose set to 0 so we don't see the loading bar. Then we'll print out the loss, although it's not really important with a classification task, because there's very little interpretability with the cross entropy loss function. But let's display it to 4 decimal places format using results sub 0. So the first value returned by results by evaluate will be the loss. The second one will be the accuracy. So that'll be the first one, and let's display this as a percentage. So 2 decimal places as a percent, and then multiply this by 100 so we see it as a percent. And then AUC finally. Let's do this to 4 decimal places also. Format using this third value from results, like so. Just indent these up and take a look. Alright, wow. Look at this. Well, I've never seen this happen before. Oh, I forgot the F. Oh, there should be F's on these, so they're floats. Okay. Okay, and you can see we're doing extremely, extremely well. Both the accuracy and AUC are really high, which means we're doing well between both classes, not just in the majority class. I'm not even going to do a confusion matrix because it's just so high. We're just going to see a perfect confusion matrix. But maybe we can see how many we're getting wrong. So model.predict on x test will give us a set of predictions. And so these are probability values between 0 and 1. So the threshold is 0.5. If we have greater than 0.5 in a given location, that means positive classification. And if it's less than 0.5, negative classification. So I think we can actually just convert this into integers to get the classifications. Yeah, so 0 or 1, depending on if it will get rounded up or rounded down. And then let's squeeze this, numpy.squeeze, so we get that extra dimension off of it. So it's a one-dimensional. and we check is it equal to y-test. So are the predictions equal to the test values? And this will be a true-false. It looks like a series. And then we can sum over the falses. So what we'll do is, actually we'll say not equal, and then take the sum to see how many we got wrong. And we should also look at how many we had in total. So we got 470 incorrect out of 1700. I might be doing something wrong here because this looks like, yeah, this is 27%. So I'm doing something wrong. Maybe this is incorrect with the as type. I'll try just asking is it over 0.5 and then turning this into an array of integers. See if that works. Alright, that's more like it. Okay, so we have 14 incorrect. And 14 over 1739, if we flip this, so we do 1739 minus 14 all over 1739, we get 91.19, which is exactly what we have as the accuracy. So we're only getting 14 incorrect classifications out of a data set of 1700 examples. So the model's doing extremely well. And usually with spam classification models, something like word embeddings will definitely do the job, because all it really needs is sort of keywords that sort of indicate if there's spam in the email. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.